Hi there. In this video we're going to continue to look at finding the volume of frustums, but this time we're going to look at some slightly harder questions, initially where we're not told the height of the original pyramid that we've chopped off. Okay, so that makes it a little bit trickier, because if you recall, to find the volume of a frustum we do the big pyramid minus the small pyramid, and if we don't know the original height we actually can't find either of these particularly easily. So we'll have a look at this first example here. So there's two sort of main strategies to do this. The first way we could do it is call the original height of the pyramid h, and then do it completely algebraically to work out what the volume is, and set up an equation in h. We'll have a look at that in our second example, but just for this one I think there's a slightly more intuitive way we can do this, which I think is sort of a bit of a better way to sort of improve your understanding, but also, yeah, it's just slightly more intuitive and you can sort of see what's happening a little bit more. So the first thing we need to remember is, how did we make this frustum? Well, we started with a big pyramid and we chopped off the top. So let's just draw back that top pyramid in. I'm just going to do it slightly off to the side, but the pyramid that we've chopped off will have had a base that was 6 by 8. Okay, now not a very good drawing, but it doesn't really need to be for this. So what we've done is we've had a big pyramid with a base that was 12 by 9, and we've cut off this top pyramid which has a base which is 6 by 8. Now you'll recall from our last video that if we chop the top of a pyramid off, it's similar to the whole thing. So if we can work out what the scale factor is between the whole pyramid and this small pyramid, then we can work out the height, we can work out what the volumes are. So let's do that first of all. So remember, if we're scaling something, we're timesing all the lengths by the same number. So we need to think, well, how do I get from this 12? How do I get from that 12 to this length here, which is 8? And how do I get from this 9 to this length here, which is 6? Now this sort of just confirms it's a pyramid for it as well, because if it's not a pyramid, or if these two numbers aren't the same, then it won't be a pyramid, it won't meet at a point, it'll be like a pitched roof on a house, it'll meet at like a line. So it does just sort of confirm this is a pyramid as well. Now to get from 12 to 8, I times by 2/3, find a third of 12 and then times it by 2, I get 8, and similarly timesing by 2/3 to get from 9 to 6. So I know that this small pyramid is 2/3 of the height of the whole pyramid, which means that this 5 has to be the other third, right? If the top bit's 2/3, this bottom bit is 1/3. So the 5 is 1/3 of the original height. Which means the original height must have been 15, 5 times by 3. So the full height, let's just write these down. So full h is 15, and the small pyramid has a height of 10. Actually I'll do that in green, just so it's consistent with this. Okay, so the height of the full pyramid is 15, the height of the small pyramid is 10. Now we can use our method from last video to start chipping away at this problem. So the big volume is the area of a third times by the area of the base, which is 9 times 12, times by the full height, which is 15. And 9 times 12 is 72, third of 15 is 5, and 5 72s are 360. So that's 360 centimetres cubed. The volume of my small pyramid, V small, is going to be a third times by 6 times 8, which is the area of the base, times by the height of the small pyramid, which is 10. And well, a third of 6 is 2, times by 8 is 16, times by 10 is 160. So my volume of the frustum is the big volume, take away the small volume. So you get 360 minus 160, and that gives me a final answer of 200 centimetres cubed. Because we'll assume all these were in centimetres. We'll pretend I said that at the start. Good. So a slightly more tricky problem, but this first method is using scale factors and identifying what the scale factor and how big this top pyramid was compared to the whole pyramid. Okay, so in this question, we're given a conic frustum this time. Again, we're not told the height of the original cone, but we do have all the measurements that we need to solve this. Now the numbers aren't quite as nice, so it's not going to work out quite as nicely. And in fact, in real life, numbers aren't going to be nice all the time. And in fact, this is the measurements of one of these little IKEA bowls. Again, lots of mugs, lots of bowls are a frustum shape. So if you've got a shape like this at home that you're interested to find the volume of, then this is a method to do it. Okay, so let's have a look then at how we solve this. So again, we'd like to work out the height of the original cone. Now, in this one, because the numbers aren't quite as nice, it's not quite as easy to just intuit and see what the scale factors are going to be. So what I'm going to do is I'm going to call the height of the original cone h big, and I'm going to call the height of the cone that we took off h small. Okay, now what we're going to be able to do is we're going to set up a scale factor system like we did before, but this time we're going to just use a little bit of algebra, a little bit. It's going to be a little bit less clear and a little bit less obvious working out our scale factor. So what we know is that the ratio between the big scale factor and the small scale factor, or the big height and the small height, is the same as the ratio to the big width, or the big diameter to the small diameter. So what we know is that h big divided by h small is going to be equal to 13.3 over 7.7. Okay, so that's going to be our first step, and that just comes from the fact that these shapes are similar. Okay, now the next thing we should be able to notice is that actually h big is just h small plus 9.1. So what I'm going to do is I'm going to swap this h big with an h small plus 9.1 over h small is equal to 13.3 over 7.7. Now a few of you might have sort of spotted that we probably could have done this without labelling h small and h big and just use it doing h plus 9.1 over h. That's absolutely fine. I did just want to label this on just to make it really clear exactly what we're doing and exactly where this h small plus 9.1 has come from. But at this point, what I'll do is so I don't have to keep writing out h small, I'll call h small just h. I'll still keep the subscript on h big, but I'll just call h small h, so that we can just use h. And then when we want to work at h big, we've got a separate notation for that. Okay, so now we've got an equation that we can solve. H plus 9.1 over h equals 13.3 over 7.7. So let's multiply both sides by h. H plus 9.1 equals h times by 13.3 over 7.7. Let's simplify that fraction down. 13.3 over 7.7. We can use our calculator function on our calculator. 13.3 over 7.7 simplifies down to 19 over 11. So I've got h plus 9.1 equals 19 over 11h. Okay, so this is more than one h, importantly. So what I'll do is I'll just subtract this h from both sides. So we get 9.1 is equal to, well, 19 11/8 11ths h minus 1h is going to be 8 11ths h. Okay, so then our last step is to multiply by the reciprocal of this fraction, and we get 9.1 over 8 times by 11. Let's write that out slightly differently. 9.1 times by 11/8 is equal to h. 9.1 times by 11/8 we can work out as being 12.5125. Brilliant. Okay, so a little bit of algebra there. Once we've got it set up at the start, this is sort of a bit like algebra autopilot. If you're at the point in your maths where you're trying to answer something like this, our algebra should be pretty secure. But yeah, at that point it is just solving for h. So now we've worked out what h is, let's go on and actually finish answering this question and work out the volume of this little cup. Yeah. Okay, so what I've done is I've just drawn the little cone that we've chopped off at the top here, 12.5125 in height, and 9.1 here. Just so it's really obvious that when we work out the whole height of the cone, V big, we have to add these two together. So let's work out V big. So the volume of the big cone is 1/3 times by pi r squared. Now again, the radius isn't 13.3, that's the diameter. So we need to half that and we get 6.65. 6.65 squared times pi times by the height of the big cone, which is 12.5125 plus 9.1, which gives me 21.6125. Now we can just type that into our calculator. And I will just do, I will do this exactly to start with, 6.65 squared times 21.6125. I'll round that, that's times by 3.14, gives me, look at that, so that's approximately equal to 1000.36 to 2 decimal places. So that is the volume of my big cone. Now let's work out the volume of the small cone. And I think the volume of the small cone is probably slightly easier to work out because the measurements we're given are a bit more direct. We don't need to worry about working out the height of the big cone. So let's work that out now. So it's going to be 1/3 times by pi times the radius squared. Now the radius here is half of 7.7, which is 3.85 times pi times by the height of the small cone, 12.5125. And so again, if we work that out, we get 1/3 times by 3.85 squared times by pi times by 12.5125, and that gives me an answer of 194.12. Just go to 2 decimal places there. So then our final answer, the volume of the whole thing, is 1000.36. Take away 194.12. Now since we're already using a calculator, I might as well use it. 194.12, which is equal to 806.24 centimetres cubed. Okay, so the volume of this little guy, now this is the external volume, so it's probably not its capacity. The volume of this guy, 806.24 centimetres cubed. So again, a really, quite an in-depth question. I would implore you to actually practice this at home. Find a mug, or find a glass or a bowl or something that you can work out the volume of. It's a really useful exercise in using some real world numbers.